I just posted a video about covalent bonds, and from covalent bonds I want to talk a little bit now about ionic bonds. So I said that when you look at the electronegativity values, remember this is the Linus Pauling's electronegativity chart here, that if there's a big enough difference between the electronegativities, or how much one element wants to pull electrons away from another, if there's a big enough difference between them, then it's a polar covalent bond. But with metals and nonmetals, which is what we have going on in ionic bonds, so metals that are on the left-hand side of my periodic table with nonmetals on the right, there's such a large difference between their electronegativities that the more electronegative nonmetal will completely rip away an electron from our less electronegative metals. And that's an ionic bond. That's when an ionic bond forms. So an ionic bond is between a metal and a nonmetal. So whenever you see in a chemical formula that you have a metal with a nonmetal, then you know it's going to be an ionic bond. Okay, so that's a good clue. You can also determine it using the electronegativities, which we'll get into later. And the other thing that's important is if we're transferring electrons, which is what an ionic bond is, so we have between a metal and a nonmetal resulting from a transfer of electrons. Now this is different than a covalent bond. A covalent bond is shared electrons, and ionic bonds are transferring electrons. So for example, we have sodium, which is in our alkali metals. So if we look at our periodic table, sodium is over here in our alkali metal column, column 1, which means that it has one valence electron. So here's our Lewis dot structure for sodium. And if we take chlorine, chlorine again is a halogen. It's in column 7A or 17 right here. Okay, so it has 7 valence electrons. Then if we were thinking about this in terms of nonmetals with nonmetals, we would say, oh, well, we could just share this one, but this isn't how it works with metals. Okay, if we have metals and nonmetals, then this chlorine is so much more electronegative than the sodium that it takes this one away. So this one is transferred from sodium to chlorine. Okay, and the resulting Lewis dot structure, if you will, is now sodium with no electron and chlorine with an extra one. Now, if I have one fewer negative charge, so I've lost a negative charge, that makes me overall positive, right? So you lose a negative and you get a positive charge. And if you gain a negative, you get one more minus sign, then you become negatively charged. So this transfer of electrons from the metal to the nonmetal, and it's always from the metal to the nonmetal. The metal always loses an electron and the nonmetal gains an electron. That means that the metal always becomes positive because it's losing negative charge, and the nonmetal becomes negative because it's gaining negative charge. Okay? Now sodium then we call a cation. This is a positively charged atom, or a positively charged ion. Ion in general just means a charged atom. So when that charge happens to be positive, whether it's a +1 or a +3, it will still be a cation. Okay. Chlorine, when it has a -1 charge on it, is an anion. It's a charged atom, so it's an ion, and the negative charge is from that "and" there. It's a negatively charged ion. Okay, so cations and anions. So an ionic bond then is a bond that comes because of the attraction between the positively charged cation and the negatively charged anion. Okay, so this resulting attraction between opposite charges is your ionic bond. when I put these two things together, then this should be a compound that you recognize, because my sodium is positive, my chlorine is negative. I get NaCl, sodium chloride. That's table salt. Okay, so when I put together my two ions, I ended up with a compound. This chemical compound doesn't have any charges. Note that I didn't bring over the positive sign or the negative sign, because when I put together the positive and the negative, then they even each other out. They balance out. And so an ionic compound, the result of this transfer of electrons, is neutral, meaning that it has no charge when you put together the cations with the anions. So I want to practice with this a little bit in this lecture. Now it's fairly straightforward when you have the same charge. When I have a positive 1 sodium ion and a negative 1 chloride ion, then that's pretty easy to balance each other out. But let's say I have magnesium, for instance. Okay, magnesium is one of our alkaline earth metals. It's in column 2 here, alkaline earth metals. So that means that it has 2 valence electrons. Okay. And if I was to pair magnesium with something like fluorine, fluorine is over here in our halogens column, so that means that it has the same number of valence electrons as chlorine, which we said was 7. Then fluorine is very electronegative, so fluorine is going to pull this electron away, and now it has a full octet. Okay? So that's all well and good, but this magnesium still has an electron, so it's not going to be happy just having 1 electron in its valence. So if another fluorine happens to come along, also the most electronegative element on the periodic table, so it's going to pull on this electron. And now this fluorine is happy, it has 8, it has a full octet. This fluorine is happy, it has a full octet. This magnesium is happy because it got rid of these 2 valence electrons that were causing it to be a little bit cattywampus. And now this fluorine has a -1 charge, because I have an extra electron here. So this becomes an F-. This 2 becomes an F-. And because I lost 2 negative charges here, that makes the charge on my magnesium 2+. So now my 2+ magnesium is going to be attracted to this fluoride, and this 2+ magnesium will be attracted to this fluoride, and now the bond that forms between them is going to be 2 fluorines for every 1 magnesium, and we would write the chemical formula like this: 1 magnesium, remember the numbers next to it tell how many are in that compound, so if there's no number, that means there's 1 magnesium and 2 fluoride. And this is the only way that magnesium and fluorine can fit together, because magnesium is always going to want to lose those 2 electrons, giving it a 2+ charge, and this fluorine is always going to want to pick up an electron, giving it a -1 charge as the fluoride ion. This means then, if we know our Lewis dot structures, we can predict what each of the charges are going to be going across the periodic table. So if we have our periodic table in front of us, which I know this is super tiny, then I'm going to make this larger. Remember that lithium is in column 1. I'm just going to go across the second period here. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon, which is our noble gas, which we don't worry about. It already has a full valence. Then I know that lithium has 1, so when it loses that 1 valence electron, then it's becoming 1 positive, so it becomes lithium plus, and that's true of everything that's in that first column. So that whole first column is going to form +1 ions. So if you have your periodic tables in front of you, or if you have them in your book somewhere, you may want to note that down, that everything in this column is going to be a +1 ion. If you look to column 2 or group 2, which is your alkaline earth metals, they have 2 valence electrons. So when we get rid of those 2, like we did with our magnesium up there, then we end up forming a 2+ ion. And that's going to be true of everything in that whole column. Now, again, with our transition metals, we can't use the Lewis dot structures to talk about the transition metals. It gets a little bit different. So we go back over to our main group elements, starting with column 13, or 3A. So boron has 3 valence electrons. It's easier to lose 3 than it is to pick up 5, because remember, the name of the game for this is to get a full octet. So if I lose those 3, that gives me a 3+ ion. And everything that is in that column that's above the stair step of metalloids is going to be a 3+. If we look at 14, carbon has 4 valence electrons, so if we're thinking about forming a charge, it's just as likely that it could lose those 4 as it is to gain 4. So if you lose 4, then you become a +4, and if you gain 4, you become a -4. Now, carbon and silicon, which are the two that this would apply to, don't usually form ions, or at least not as often, so we don't tend to think about them in ionic compounds. Silicon much more so than carbon, but this is the general pattern. Nitrogen has 5 valence electrons, so we have the non-bonding lone pair there in 3 places that it could bond if we're thinking about it like a covalent bond. But if we're thinking about it like an ion, it could pick up 1, 2, 3 electrons and become negatively 3 charged, right? If I add 3 electrons, that gives me a 3- extra. So everything in this column is going to do that. Oxygen has 6 valence electrons. Sorry for kind of squeezing these in. That's 2 lone pairs and 2 individual electrons. So if I add 2 electrons here, oxygen's very electronegative, so if it pulls electrons away from a metal, then it makes it a 2- charge, and that's going to be true of everything in that column. And then I go over to my halogens, fluorine, and I have 7 valence electrons again. And just like we saw with our magnesium fluoride up here, it likes to get an extra electron there, which makes it a negative charge, and that's true of all of the halogens. So in general, if we know our A's and B's for the column numbering, right, we said there's 2 ways of numbering it, 1 through 18, or the group A's and the group B's. If we know our group A's, then we know how many valence electrons there are, and if we know how many valence electrons there are, we can predict what the charge is going to be. Okay, so based on where it is on the periodic table, you can figure out how it's going to be transferring, gaining or losing electrons, right? So gaining on the non-metal side, losing on the metal side. Okay, so let's practice with this a little bit more. Let's take aluminum and oxygen. Now aluminum is in column 13 or 3A. It's right below boron, as 3 valence electrons. Okay, and then oxygen has 6 valence electrons, so it wants to pick up 2. So oxygen likes to form a 2- ion, and aluminum likes to get rid of those 3 electrons, giving you a 3+. Okay, so I just figured that out based on where it is on the periodic table. It has 3 valence electrons. It's easier to lose those 3 than it would be to gain 5. So that means that when I lose those 3, then aluminum becomes a 3+. And oxygen is electronegative. It's going to be pulling electrons away from other elements. So when I gain a full octet there, I have to add 2 electrons for oxygen. So that gives it a 2- charge. When I put these two things together, remember that an ionic compound has to be neutral. So that means that the charges on each of them have to balance each other out. When you add together the charges, they have to equal 0. So you have a neutral compound at the end of it. So if I just had 1 aluminum to 1 oxygen, then I would end up with a 3+ minus 2 gives me a +1 overall. So that's not good because I'm trying to get to 0. So I need to have more of each, and this one's tricky because it's not as simple as it was with the magnesium fluoride. With magnesium fluoride, I could just say this one's a 2+, this one's a 1-, so I need 2 of these for every one of these, right? It's not as simple as just multiplying. This one kind of goes to the idea in math that you've probably seen in somewhere in your academic career about lowest common multiples, right? It's the number that both of these numbers go into and will give you what they will both what they both can divide into, right? So in this case, for 3 and 2, it's 6. So to get aluminum to 2, or to get, give it away. To get aluminum to 6, I need to multiply by 2. And to get my oxygen to 6, I need to multiply by 3. So when I put these together, I end up with Al2, that's 2 times my 3 plus O3. So aluminum oxide, Al2O3. Again, the subscript's telling me how many of that element that they're following. Okay. So the key to ionic compounds and the key to figuring this stuff out is knowing on the periodic table which charges are which. So everything in column 1 is +1, and column 2 it's +2, column 3 is +3, +4, -4, -3, -2, -1, 0. So if you know all of these, when I ask you to put them together, so let's say potassium with sulfur, potassium with sulfur, then you can go to the periodic table and you say, well, I know that potassium is a metal. It's one of my alkali metals. It's in column 1, so it's a +1 charge. Sulfur is in the same column as oxygen. It's one of my chalcogens. It's in column 16 or 6A. So that means that it has 6 valence electrons, so it's going to pick up 2. So when I put them together, what is the chemical formula going to be? Remember that we need to balance out the charges on this. So in order to balance out the charges, I'll need 2 of my +1 for every 1 of my -2. So when I put them together, I get 2 of my +1 for every 1 of my -2. And this would be my chemical compound. And this is the only way that I can put together potassium and sulfur. Okay, so that's ionic bonding. Now I want to relate this back to what we talked about with the electronegativities of our elements. Before, I said with our electronegativities and the scale that we use, the Pauling electronegativity scale, that if it's less than 0.4, then that means that it's a non-polar covalent bond. Okay, so less than 0.4 means that they're so close to each other that it's basically an equal sharing. I said if it's between that 0.4 and 1.7, then we have a polar covalent bond. So there's enough of a difference between them that one is going to be pulling on those electrons more than the other. It's going to be a little bit of a shift, okay, from one side to the other. And then now, if it's greater than this 1.7, this is going to mean that we have an ionic bond. There's so much of a difference in the electronegativities that that nonmetal is going to be ripping those electrons away from the metal. That means that there's a transfer of electrons from one to the other. And that transfer of electrons results in charges. And then these opposite charges attract, and that attraction causes this ionic bond. Okay, so that's how we can relate this back to the electronegativities. If you wanted to see an example of this, let's break out the electronegativity chart again. So if we take calcium, for instance, if I wanted to put calcium and, let's do calcium and bromine together. When I look at my electronegativity chart, calcium is 1.0, bromine is 2.8, bromine is my nonmetal, calcium is a metal. So just right off the bat, I know because it's a metal with a nonmetal that it's an ionic bond. But if we're comparing it using our electronegativities, I take the small one from the large one, and I end up with a difference of 1.8. 1.8 is greater than my 1.7, which means the bond is ionic. Now the Pauling electronegativity scale is very handy, but it's not the be-all end-all. Sometimes you'll find that these numbers aren't 100% accurate all the time. They do give a general model and a good one, but this isn't the only thing that you should be thinking about. If you have a metal with a nonmetal, then it has to be an ionic bond. That is always true. If you have a nonmetal with a nonmetal, it has to be a covalent bond. So even if the difference is greater than 1.7, which it can be because fluorine is so electronegative, then it's still going to be a polar covalent bond because it's sharing of electrons, not transfer of electrons. So that's the difference between our polar covalent bonds and our ionic bonds that we talked about here. Okay, as always, if you have any questions on this, just let me know, and otherwise I'll talk to you soon.